There we go. Oops. Shifting things around here. Whoa. Looks like there are some people here. Just if anyone's here, just give me a message in the chat if you can hear me. It's my first time using Hopin, so I just want to make sure I set up everything correctly. Awesome. Thanks, guys. And while we're waiting, for those of you who are here, maybe give like a brief introduction. Like I'm curious to see what background you guys are, like what field you're studying, you know, what year you're in, and what brought you to this workshop, just anything. So I'll break the ice a little bit. I'll start a little bit about myself. Looks like we got 6 people here, I guess. But yeah, so, and I'll say this in the workshop as well, but my name is Hosak, and I go to U Waterloo, and I'm in data science. So I actually made a switch from mathematical physics to data science. just because during my first co-op, I worked with a very brilliant professor named Anita Layton, and she kind of got me into machine learning. I actually did a project on autism research and using AI to aid in the autism research. So that was really cool, and it just kind of made me realize that artificial intelligence is around us everywhere. Its purposes can be used very creatively around us. So um, that's honestly one of my favorite things about data science is to be able to collaborate, and learn and teach others too. I've always had a passion for teaching. So yeah, honestly, I'm really grateful for this opportunity to be at the workshop today. So thank you, Theo, for reaching out. Just gonna stop sharing for a sec. You know what? Why don't I actually gonna post the notebook in the Discord chat. Is there by chance a workshop slides and oh yeah, I can do it after as well. Let's see if I can do this now. I see we have more people here. That's awesome. It's a total of 9. So um, as I was saying before, if you guys just want to like give a quick tidbit about yourself as we go through the workshop, feel free. I'm always curious to see where like what kind of backgrounds you guys are from. Like if you're like what kind of year you're in, what things you're studying. Um, so just feel free to like tell a little bit about yourself. Yeah, because we're gonna probably be waiting a couple minutes for more people to come in. Theo, just give me a heads up when you guys are good to start. Nice. Second year McMaster studying health and engineering science. That's awesome. Yeah, I don't know. I think I'm not sure what the closest equivalent program we have at Waterloo is, but there's lots of different kinds of engineering at Waterloo. I have to familiarize myself more with it, but that sounds amazing. It's got 10 people now. First year student at Queen's University studying CS. Awesome. Very nice. Honors Life Science having master. Very nice. So cool to see people like of different backgrounds. Like some of you are from CS, like math, first year and student at Mac. health sciences, life science, lots of different backgrounds. So please feel free to keep posting these, and I'm gonna get started. Unless Theo, did you want to like do any pre-workshop work? But just let me know, and I will, I guess, start us off. So first of all, again, thank you to Theodore Liu for reaching out to me and inviting me to be a speaker at this workshop today. So as mentioned before, a little bit about me. My name is Hosak, and I'll be your host for this workshop today. So this is the Intro to Neural Networks workshop. And so I really can't wait to see what kind of project you guys come up with. I'm super excited because I just joined the Discord and I'm already seeing some great ideas bouncing around. So this is absolutely amazing. And it's amazing that you guys took the time out of your day to come to this workshop on your weekend and to just learn about new things. And there's something really rewarding about learning about, especially about artificial intelligence, since it's honestly such a rapidly developing and growing field. I mean, even in the 60s, we had very little knowledge about AI. Our understanding of how to implement AI was extremely primitive, as I'll discuss in this workshop. But I commend you all for being here today and taking this initiative. So thank you, everyone. So my name is Hosak, and I'm a third-year data science student at the University of Waterloo. So I actually switched from mathematical physics to data science just because I realized how applicable data science was as a field. It's very applicable to a lot of different fields such as finance, medicine. One of my previous co-ops was with autism research and how I can use AI to aid in semantic image segmentation for helping with autism spectrum disorder research. Now, I've had a bit of experience with building, training, and testing neural network models. And one of my especially favorite research areas of interest is how to watermark these models. These models are by nature supposed to be very dynamic. And as a result, you can't just slap on a stamp or a watermark and say that it's authenticated, because that watermark might disappear once you try to use it for transfer learning or to keep training on a different data set. So that's kind of the things you could do with neural networks. There are so many different applications, and I want to give you a quick overview of the structure of this workshop. So I understand some of you have a little more background in AI than others, and that's totally fine, because we'll be reviewing the concepts of AI and neural networks in the first half of this workshop anyway. And I understand that there was a data pre-processing workshop going on earlier, so I won't go too much into that. However, I do want to kind of give an example of the sort of ad hoc processes of analyzing and pre-processing this data, readying it for the neural network to train on and test on as well. Okay, so I should note that we will be using the TensorFlow machine learning framework. Why TensorFlow? Well, because it is one of the most advanced and established frameworks out there. From my understanding, it was one of the, maybe not one of the first, it could be, but one of the most advanced for sure. So the reason why we're using TensorFlow as opposed to like PyTorch or something is just because in my experience, TensorFlow is pretty beginner friendly. So this is a nice sort of segue into an introduction to neural networks. So in this workshop, we're going to be discussing a very particular kind of neural network. It's called the convolutional neural network. Now, what convolutional neural network means is it applies the operation of matrix convolution to an input, which is in the form of a multidimensional matrix. So if you don't understand what those terms mean, that's totally okay. I'm going to go over those in that workshop. That's what I'm here for. Okay. So this project, the reason why we're employing a CNN is because I used to love the Simpsons show, watching that growing up. I don't know if you've ever watched it, but it's basically a show about a family of 5 who lives in Springfield, Illinois, and it's a cartoon show. So I actually went to Kaggle.com, which is a huge site for finding datasets. I would definitely recommend checking it out if you haven't already. Many datasets can be found via searching on Kaggle.com, and I found a image dataset containing snapshots of the Simpsons characters. So they took snapshots throughout the seasons of instances where each main character from the Simpsons appeared. So they had to kind of choose like which characters to include, and it looks like they went with the 19 most prominent characters on the show. So the goal of this project is to develop a convolutional neural network that can take in images of the snapshots of the characters, and it can correctly identify which character is being shown. So I'm going to go through an example of what our objective should be soon in this workshop. So again, quick note about Kaggle. You can also use Google Collab for coding up your models. You can code up your models in Kaggle as well. I'm going to use Google Collab just because I feel like it's a pretty beginner-friendly interface. So yeah, our workshop outline. I'm going to share my screen now. So, and if anyone cannot see the notebook here, just give me a heads up in the chat. But here I am showing the outline for the workshop. We're going to go through artificial intelligence and neural networks. What do they actually mean? And then we're going to go through, importantly, how image data is represented in Python. And we need to know this because we need to be able to convert this image data into numbers. These numbers are what's going to cause our model to be able to learn, right? This model, you will find out that it's basically just a huge number crunching machine, right? At its very simplest level. Then we'll go over convolution and max pooling operations. What do they actually do for us? Why are they important? And we'll also go through 6 and 7s. These sections are really important. I want to walk through these sections with you guys. So data normalization. Why is it important to normalize your data? And what is the significance of the bias variance trade-off? Like, what is it in statistics? Some of you may have heard of it, but I will go over what it exactly entails and how does that apply to our convolutional neural network project. Model architecture. We'll just quickly be going through the idea of convolutional blocks, how to employ these convolutional blocks to build like a nice flow of data through the network and coming to a prediction. And finally, we'll optimize the model in its performance as well as generalizability. Okay. So without further ado, let's begin. Before we continue, I think there's a question. I heard CNN is really good for image processing. Is there any reason why we prefer one over the other, or is that really just based on the package library being used? Great question. So I would say that CNNs are really good at processing image data just because of the way that they're implemented. So for example, if you look at the matrix convolution operation, we'll find out that it's really good for finding patterns. The idea is that when you analyze images, you want to kind of create a summary of defining characteristics of each, in this case, Simpsons character we want to classify. So I would argue that it doesn't really depend on the package so much as the understanding of how these layers work and the models. And again, I'm still learning as well, but this is just what I've learned about convolutional neural networks. Many sources, I think, will say that convolutional neural networks are one of the best for handling visual inputs. So great question. So before we begin, you just need to install some dependencies. And this Google Collab will be posted in the Discord chat. I believe it's being posted under the workshops channel. Using Google Collab will allow you to take advantage of the, it should include all the packages necessary for this project. So things like Tensorflow, numerical Python, matplotlib for plotting the accuracy of the model over time. We'll also be using this package, this guy right here, PIL. This is important in the first half of the workshop. It stands for Python Imaging Library. So don't worry about this section too much. You will find this in the Google Collab notebook, and it will all make a little more sense once we've completed the workshop. So first things first, when we're working with Google Collab, chances are you have some image data set. In this case, it's going to be our Simpsons character image data set that is contained in our local drive. So what I've done is I've mounted my Google Drive. And the nice thing about this is that once I've done this, that means I don't have to keep manually uploading my data set to the notebook every single time I want to run this. And that saves a lot of time because this notebook takes a really long time to bring in the data set. Why is that the case? Well, we'll see in a minute why it takes so long. And that's because images are represented as multidimensional arrays in Python, or we can think of them as tensors, right? Or matrices. And usually matrix operations take, if you want to use big O notation, order of n squared or order of n cubed or order of n to the however many layers they have. So it's quite a long process. And we want to be able to have this on the ready so that we don't have to keep uploading this every time. And of course, if you guys have any questions, just feel free to post them in the chat. I'll try and get to as many as I can. So now that we've downloaded our dataset, we can actually get a glimpse of our Simpsons image dataset. And the way we're going to do that is call os.listdir on the file name path to all of our test images. Okay, so the way that our dataset is structured is that it has the Simpsons image dataset. Inside are two folders. There's the training images and there's the testing images. And for each of those training testing images folders, there are 19 subfolders. Each one corresponds to a character from The Simpsons. And so we have indeed 19 characters, and these serve as the classification options or categories that our model is trying to predict for each of its inputs. So for example, if you give an image of Bart Simpson, you'd want the model to say, hey, this looks like Bart Simpson. Or if you give it a picture of Homer, you want to say it's Homer, and so on and so forth. So I want you to notice that we've created this sort of resized train path and resized test path variables. What do those actually mean? Why do they need them? Well, it turns out that convolutional neural networks, one of the downsides is that they can only take in inputs of fixed size. So we need to resize these images so that they're all the same size so we can properly analyze using the CNN. So we're going to resize the 512 by 512 pixels just because not all the images are 512 by 512, but they usually are around that size. And it's a pretty popular size and it's very easy to work with. So we're going to use 512 by 512. And it turns out the actual size of the image when represented as a NumPy array is going to be 512 by 512 by 3. Why is that the case? Well, because these images are RGB based. So red, green, blue. That means they have inside each pixel is actually represented as 3 data points. So one for how much red channel, green channel, and the blue channel. So let's get started with a little bit of AI and neural network recap. So what exactly is artificial intelligence on a high level? Like, why do we need it, and what are neural networks? Well, AI and NNs, or neural networks, they're kind of synonymous nowadays. They're kind of buzzwords that we throw around in a resume, maybe, or like if you're looking on Coursera, you see tons of courses on intro to neural networks, artificial intelligence, deep learning. What do all these terms mean? Well, they all kind of mean the same thing in a way, because back in the day, we used to have expert systems, and expert systems were an attempt by computer scientists to summarize human logic as a whole bunch of if-else statements, facts and rules, which didn't exactly work out. But this was called symbolic AI. And symbolic AI is now a defunct field of study. But nonetheless, we were still able to draw some inspiration from the field of study of symbolic AI. And we said, well, this led us to deep learning and neural networks, right? We decided to say, well, instead of if-else statements, why don't we have something that can learn a function without being explicitly programmed to do so? And in particular, we want a model that can perform on a huge data scale. So these are what neural networks do. They're deep learning models. So some of you may know this already, but a neural network is a massive collection of neurons, right? And these neurons are basically just, well, weights and biases. They're numbers. So you can think of a neural network as this huge number crunching machine, right? It takes an input as numbers, does some things to those numbers, and outputs more numbers, right? So that's a huge oversimplification, but that's essentially what it's doing on a very intuitive level. So it's kind of modeled after the human brain. We have individual neurons which choose to activate based on their inputs and their own set of rules. And these outputs, these activations serve as new inputs for other neurons in our brain. So in the same way, let's look at what a neuron might look like in a neural network. So as you can see, we have what's called weights. And weights are the properties not of the neurons themselves, but of previous neural activations to the current neuron. They are a property of the connection. Whereas biases, so a bias is kind of a rule that says if the weighted sum of the inputs exceeds some value, then I will activate, otherwise I will not. That's what the bias says. The bias is kind of this rule for activation. That's a property of the neuron. So I'll repeat that once more. Weights are a property of the interneuron connections. Biases are a property of the neurons. So how this works is it's basically just multivariate linear regression, right? So if you've done statistics and multivariate linear regression, you say, well, we have a constant term or an intercept, then we have all these different polynomial coefficients for x1, x2, blah, 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 xn minus 1, xn. And the way that this works is that after you take the weighted sum of all the outputs from the previous neurons in the previous layer, So neurons that have activated beforehand, and now you're considering these activations as new inputs, take the weighted sum, then feed it to some step function. And you say, well, if my weighted sum exceeds some value, then I will activate, otherwise I will not. Okay. Now it turns out that we need something other than this Heaviside function. We need what's called the sig point function, because the sig point function is differentiable. Now the question is, why is it important for our function to be differentiable before we give our output? Well, the reason is because where does the learning actually happen? Well, the learning is done through a process called backpropagation. So the way that backpropagation works is that you have some loss function you're trying to minimize. And this loss function gives the value of your error when the model gives a prediction, and it compares it to the true or correct value. We also call this the label of the inputs. And we say, well, depending on how far off these are, we give an error rate. And we are trying to minimize this error rate. Now, how do we minimize functions? We can use multivariable calculus, right? And we can calculate the gradient vector of this loss function, which gives the direction of the steepest descent. And so the idea is, well, for each of these weights and biases, we're going to take the partial derivative, which is an element of the gradient vector, which is a partial derivative of the loss function with respect to this weight or bias, and we're going to minimize it in a small step in that direction. So an intuitive way to think about this is, well, imagine you're on top of a hill. And if you're on top of a hill, then imagine you're blindfolded or it's dark outside and you can't see where you're going, but you want to get to the bottom of the hill as quickly as possible. So your strategy might be, well, I'm going to first determine the direction of steepest descent down the hill because I want to get down as quickly as possible. But I don't want to trip and fall, so I'm going to take little baby steps in the direction of the steepest descent. And so that's what's going on here, is that, well, we're taking little baby steps towards the optimal performance of the model. Also, I see the link is not accessible for the Google Collab notebook. I will, after this workshop, make sure it's accessible. Maybe some editing properties or sharing properties need to be fixed. Let me go in right now, actually, and anyone with the link? Okay, so if you guys try clicking on the link now, it may be accessible. Let me know in the comments, as always, if it's not. So I'm going to move on and talk about the image representation in Python. Okay, great, the link works, good. So the way we're going to do this is, well, how exactly are images represented in Python? Well, first we show its raw value, so the actual image. So first what I'm going to do, and I'll explain why I'm doing this in a minute. If you guys don't know what a GPU is, it is a graphic processing unit. It works really well with machine learning, just because GPUs allow you to work a lot faster on your model training. And these models can usually take months or even years to train, and that's not really what we want, right? We don't want to be wasting away in front of a computer screen. We want time to do other things. Okay. So gonna run these one by one. So again, run our imports, mount our Google Drive, and now we are going to get a glimpse of our Simpsons image dataset. So here are all the classes for classification. Now we've been through the artificial intelligence and neural networks recap. Again, a neural network is just a huge collection of number crunching numbers, right? And the learning happens through gradient descent. Now, how do we represent image data in Python? Well, here, what we're going to do is open up a sample image, and let's take a look at its raw metadata. So as we can see, this is an image of Bart Simpson. And we say, well, what is the image size, or what is its dimensions in pixels? And it's 640 by 480. So that's all good and fair. Now we want to convert this to a NumPy array. And how is it expressed as an array? And we see this additional 3 here. What does that 3 mean? Well, as I discussed earlier, these images are RGB based. That means that they have each pixel is represented by 3 channels. So one for the red channel, one for the green, and one for the blue. So we need to somehow process the images so that we can turn them into fixed size arrays. So the first step to do is resize the images. Well, I'm going to set the global variable here called dim, so that in case we need to change the dimension of the image, we can easily do that. The number of classes is 19. And what I'm doing here is I'm basically saying, well, if it doesn't already exist, make a new directory. Make a new directory dedicated to resize, training, and testing images, so that if it's already created, we could just skip over this step. In this case, it turns out that the directories are already created, but it's resizing all the images and collectively putting them in these two directories. Okay. So now if we go to this directory and try to access the same image, we can see that the image size and the NumPy array representation, the size should have changed. So it's now 512 by 512, as we expect. Very good. So now that the images have been resized, we can store the resized image files into lists, right? So why are we storing the file names into lists? Well, the reason we want to do this is because we don't want to turn these into arrays right away. And the reason we don't want to do that is because we want to kind of take a just-in-time approach, in the sense that these NumPy arrays can take lots of memory, right? So it turns out that in your Google Collab environment, you only have 16 gigs of RAM, and you don't really want to take up this RAM unnecessarily, right? It's precious memory. So you want to kind of practice a little bit of memory and resource conservation. So I'm going to leave these as lists of strings for now, because lists of strings take a lot less memory than NumPy arrays. So what I'm going to do is I define this function here, and this is kind of the this is kind of useful for data preprocessing, is defining helper functions so that it can easily take your data and turn it into a format that's easy for you to handle. So the format that I'm using is here xtrain is a list of all the image names that are located in the resize train directory. Similarly for xtest, it's the list of all the names for the images in the xtest directory for resized images. Meanwhile, ytrain and ytest, this is where we start doing something known as one hot encoding. And what is one hot encoding? The one hot part comes from the fact that if you have an array of bits, which are all set to 0, so recall that bits can either be 0 or 1. One hot means that we set exactly one bit to 1, or hot, right? So one bit is 1, everything else is 0. And the reason why we do this is because, well, we have 19 classes we're trying to classify across. So the idea is, well, why don't we represent each category by the corresponding index of an array of 19 zeros where the 0 has been turned to a 1. So here's an example. If Bart Simpson is encoded to the integer 0, and Homer Simpson is encoded to the integer 1, and we can encode all these classes from 0 to 18, then if we want to indicate that a label is Bart Simpson, well, since Bart Simpson was encoded to 0, then we set the 0th index, or the first element of that list to 1. If we had Homer encoded to 1, then we take that array and we set index 1, or the second element, to 1, and so on and so forth. And so that's what we're doing here. And the question is, well, why don't we just make the outputs integers instead? Why don't we say, well, the y prediction should be some sort of integer? Well, it turns out that when we're doing matrix multiplication and linear regression and all this statistical analysis, it turns out that we can get a problem of not only exploiting gradients, but just messed up in outputs as well. Because the way that the neural network tries to analyze the data is it tries to find sort of clusterings or patterns of data. And so we don't really want this notion of distance or magnitude in our data. It's better to have, because these character categories don't really have an ordinal aspect to them. They're not really one is greater than the other. So instead, I figured it might be better to one hot encode. So have a huge matrix of zeros and ones. Now, this will take up a little more memory, yes, but I'm willing to make that sacrifice just because zeros and ones will lend itself a lot better to machine learning than, in this case anyway, than for an ordinal scale such as integers from 0 to 18. Since these characters don't really have an ordinal structure themselves, so I want to maintain that lack of ordinality. So this is kind of what you have to think about when you consider how to encode your string data. Okay. So the other thing we need to consider is there is a severe class imbalance, or there will be. How do we know this? Well, generally with shows, we have protagonists or main characters. And these main characters are going to get a lot more screen time than the minor characters, right? So within these 19 characters, there are probably, maybe 3 or 4 characters who get the most screen time, and some of them don't get as much. So we want to consider that. That means that the proportion of images for which these minor characters show up is less in the image data set than for the protagonists. So how do we deal with this class imbalance? Well, we can kind of approach it in 2 different ways that I see it. First, we can undercompensate on the protagonists. So any images that show the main characters, we can omit some of them to account for this class imbalance or the lack of images for the minor characters. Or we can do what's called creating synthetic data. And synthetic data is where you take the images that are kind of lacking or the classes that are kind of lacking, and you create fake data for it. Now, how do we do that with images? Well, you can like rotate, you can invert, you can flip the images, kind of like move them in a way so that the machine learning model treats it as a completely different input while still holding the same character inside. But for the sake of simplicity, we're just going to go with omitting some of the extra images or the excess images of these main character subfolders. So what do we mean with that? So for example, Homer Simpson is one of the main characters in the show. So he's going to have a lot of images associated with him. That means we got to take out most of those images to account for the fact that some of the minor characters only have maybe 100 to 200 images inside. So the way I do this is, well, I'm going to print out how many images are there for each character in this data set. And then I'm going to print that list and say, well, let's declare a variable m. And m is going to be the minimum of this list. Why do we take the minimum? Well, because we're going to recreate our training data so that every single character has exactly m images, so that we contain all of the image data for the most minor character, and every other character will have the exact amount of images as that character. So that way we're completely eliminating the class balance. Now, this isn't an optimal way to do it because generally more data tends to be better within reason for machine learning. But for the sake of simplicity, I'm going to do it this way. Again, I am omitting the extra images for the main character so that we have an equal amount of training data for each category. That's how the machine learning model will work best. Because if you have too many images for one of the characters, then it's going to overtrain on those particular classes and will not have enough exposure to the other characters. So its accuracy is going to get way thrown off. So congratulations, we're almost done finishing pre-processing our image data. So the final step is to convert the list of file names, xtrain, xtest, and recall this was the list of strings or file names. We're going to take that and notice that we've introduced a validation split, right? And you'll realize that validation data is actually very important for training your machine learning model. A validation data can kind of serve as a evaluation point on how well your model is doing during the training process. And then in addition to that, there's extra testing that you can do afterwards. But validation loss and accuracy can tell you a lot about how your model is overfitting and underfitting. And I'll explain why in a minute. So you may have seen the need for validation splits. I'm going to introduce a 80-20 validation split. Some people like to do 70-30. That's fine. So I printed out the number of training points here was reduced from 15,000 to only 1,600 data points. So these are the number of images in our training data. Now we're going to convert this training data into NumPy arrays. And this will take quite a long time just because NumPy arrays, again, you're dealing with O of n squared. Even with the vectorization that NumPy implements, it still takes quite a while. So now, while this is running, I want to take this opportunity to discuss what operations are we using in our model. So it's right at 2 o'clock. This is the second half of our workshop. And quick note, I just actually put in a ETA. So this says that this process will approximately finish in a little over 5 minutes because this ETA is accounting for how long will it take to convert the training data to NumPy arrays. And we have to do the same thing for testing and validation data. So I'm going to estimate about 5 to 6 minutes. Let's see how close we are on that. So if anyone has any questions so far, anything I can clarify, please feel free to post a question in the chat at this time. So I'm going to go over convolution. What exactly is convolution? How does it work? Well, in this context, we refer to matrix convolution, right? And the way it works is this. Let A be a matrix of dimensions n by n. So A is this huge matrix. Let's say it's an image, right? Image representation. And let B be a square matrix kind of a small square matrix. So it has dimensions p by p, where p is really small compared to both m and n. So to convolve A and B, you're going to do the following code. So what this code is saying intuitively is that if you have an image, imagine that you have a square sheet of colored, like tinted paper that you can see through. It's like a filter. So imagine you have a square filter, and actually, I can use the Rubik's Cube here. So imagine that this is your image, and you're going to take a little tiny submatrix of this matrix here, and you're going to apply a filter to it, right? And the way we apply a filter to this is we take the Hadamard products, or the element-wise multiplication sum of this submatrix by the filter. So the filter is defined as a small submatrix. So let's say we have the matrix, in this example, it was 1, 2, negative 1, 3. We're going to take 1, 2, negative 1, 3 and multiply it. So 1 times this value plus 2 times this value plus 1 times this value plus 3 times this value. We're going to take that weighted sum for all of the consecutive submatrices in this matrix. So if we have this submatrix, then we slide over to this window, then we slide over to this window, and we're going to keep doing that for all the possible submatrices that can fit inside this matrix. So let's run this code and see what we get after this is done. So this will take a little longer than expected. Once this code is done running, we will be able to show an example of convolution. Convolution is the core of convolutional neural networks, as the name suggests. This is because what convolution does is it kind of gives a summary of the image. It allows us to kind of reduce its dimensionality pixel-wise and instead express the image as a set of features. And so if we scroll down to our model architecture here, okay, basically what we're doing is we're saying, okay, let's input a 512 by 512 matrix as an image, or image as a matrix. Then we're going to apply 2D convolution. What that means is that we're going to take this image, so 512 by 512 by 3, and we're going to say convolve a 3 by 3 submatrix or a filter along all the possible 3 by 3 submatrices of this matrix. So here, 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 and then you slide down and do this row, and then do this row. And you're going to take the weighted sum for each of these element-wise products. So if you had 9 elements in the 3 by 3 filter, you're going to take each of those 9 elements and multiply it by the corresponding elements in this submatrix. So elements 1 times this, element 2 times this, and so on and so forth. So it's like the dot product in a way. Now, this 32 here represents, well, we're going to extract 32 important features from the image in this layer. And the next layer says 64. So take the output from this block right here, and this time we're going to take that condensed image and output 64 important features. Then we output 128 important features and 256. Then we go back down. So 128, 64, 32. Why did I decide on this architecture? I will get to that in a minute. So let's just see if this is done running. So again, as I mentioned, this will take quite a while. This cell has been running for about 4 minutes, 49 seconds now. And let me just double check that we are, yes, indeed, using a GPU. GPUs don't really affect the runtime on relatively small computations like this, where we're using only NumPy arrays. They really help when you're doing machine learning computations. Okay, so just keep that in mind. Google Collab has a GPU limit, so you can only use it for about like 12 hours, I think, or so, before it gives you an error saying you need to stop using the GPU, just because Google Collab is trying to allocate this GPU resource to a lot of different users at a time. Okay. So in the meantime, I also want to discuss max pooling. So what is max pooling? Well, imagine that we now have a convolution result. So we have a matrix that is a result of taking your image data and convolving. That means taking a filter and sliding it across each possible submatrix that fits that filter frame and taking information from that filter. Now we're going to take that convolution result and we're going to get only the most important data. And the important data here is interpreted as the maximum value within a submatrix. So again, now imagine this smaller matrix is our convolution result. So now we're going to say, well, what is the maximum value within this submatrix? What is the most important detail in this submatrix? Similarly, what is the most important detail in this submatrix and this submatrix, etc. And the maximum of those submatrices represents the most important detail. So I don't want you to get too caught up in how the operations actually work on a super deep level. If you by chance get into machine learning research, then you will have a chance to kind of examine how this works on your own. But I want to give you a high level understanding of what's going on here. So convolution is basically looking for patterns. It's applying a filter to extract 32 or 64 or however many you want important features from the image. Then you go one step further, and with max pooling, you take an overview or a summary of those important features. You say, well, from each of those features, what are some important details that we need to characterize this image as belonging to one of 19 categories? Okay. So this is what's going on here. And we can see here in our architecture that we will include both convolutional 2D and max pooling. So the max pooling 2D comes right after the convolution, right? And this is a nice flow because we say, well, after we've convolved, after we get our convolution results, so the 32 important features, we're going to take max pooling and say, what is the brief summary of that? Because we don't want to overthink small details. We don't want our model to overthink small details and get fixated on these small details and images. We want it to be able to look at the big picture quite literally and say, this image is Homer Simpson, this image is Bart Simpson, etc. Okay. So it looks like we got about 9 seconds until this image processing is complete. So it looks like this cell is running for 8 minutes, which isn't bad. Okay. So meanwhile, while this is finishing up, what I'm going to do is walk you through data normalization. Why is it important to normalize data? Well, let's think about if we have a standard image, right? Standard image, the typical values of a pixel are 0 to 255, as you know. So when we have these typical image values, we can get quite a large scale and a lot of variance in our data, right? So it could be anywhere from like 0, a really dark pixel, to 255, like a white pixel. And what does that represent? Well, it represents the amount of color or brilliance in each image, right? And so if we were to take our example from the neuron, and our inputs are like maybe anywhere ranging from 0 to 255, let's say this one was 128, this one was 254, this one was 3, then we're going to get a pretty wildly varying weighted sum that we feed into our step function to give us our output. Now, what that means is that our neural network output might be messed up as a result. It might be overthinking these small details, these fluctuations in the image data. But that fluctuation isn't actually super important because that's just how images are represented. They're by definition represented as 0 to 255 image arrays. So what we want to do is standardize our data, right? And by standardizing our data, we reduce the risk of what's called exploding gradients or model failure to learn. Now, what exploding gradients are is basically when your inputs vary so wildly and are so large that your model computes the gradient factor of your loss function to be quite a large, have quite a large magnitude, right? And as such, when your model tries to minimize when it tries to optimize all the weights and biases by minimizing this error rate, it takes too big of a step. It takes too big of a step when it's adjusting its weights and biases, and it's going to overshoot a local minimum, right? So in intuitive terms, that means that when you don't normalize your data, you're giving it really large inputs, right? Potentially. And what does it mean to give a model really large inputs? Well, it's going to treat all these values as for what they are. It's not going to say, well, hey, you didn't normalize your data. It's going to treat this as if it's the input that you intended. And as such, it's going to learn lots of different variance patterns in the data because the scale is so large. And so we want to normalize our data, so minimize the scale to minimize the amount of variance that we get in our data set. That way, the model's not going to try and learn like super like weird and wacky variance patterns in our input data set. Okay. So it looks like this finished running. Let's give an example of convolution. So as we mentioned before, this is our image matrix, and this is our submatrix, our filter. Now what we're going to do is take this element times this element, plus this times this, plus this times this, plus this times this, and we're going to repeat that for every single submatrix that occurs here. So this one, and then the 1, 2, 6, 7, and the 2, 3, 7, 8, and then the 3, 4, 8, 9, and we're going to continue that process. So for example, 0 times 1 plus 1 times 2 times 5 times minus 1 plus 6 times 3, that will be 15. And you do that for this one, you get 20, 25, 30, blah, blah, blah. Okay, so this is our convolution result. It's 15, 20, 25, 30. Notice that this image or this matrix dimensions are smaller than these ones. Okay. So that's the nice thing, is that convolution kind of gives like a summary, a brief summary of the image in terms of important features. Now, let's run max pooling now and see what we get. So we take the same matrix, so 15, 20, 25, 30, etc. And we take, well, given a 2 by 2 or less boundary, what is the maximum value in this submatrix, this submatrix, this submatrix, and this submatrix? So we're blocking it essentially. And we want to take the maximum value in each of those blocks. So the maximum value in this block is 45. The max value in this block is 55, and then similarly 70 and 80, and that's what we get here. So again, this is just taking the most important details to feed into the next layer of neurons. So it's basically saying, hey, this is what I've learned about the image. Now you go and analyze this. Then the next layer says, this is what I've learned. Now you go and analyze this. And it's a recursive process until you get to the output layer. Okay. So once again, data normalization is very important because you want to minimize the amount of weird, wacky variance patterns you have in your input data set as much as possible. So this kind of leads into our talk about bias variance trade-off and convolutional neural networks. What is the bias variance trade-off? Well, it states that if you guys have taken stats before, the bias of an estimator is basically how much error there is, right? So how far is it from the true value of the parameter of interest that you're trying to estimate? So for example, if you're trying to estimate the mean of a population, the bias would be the estimated value of the mean minus the true value of the mean, right? Now, obviously, we can't actually observe this bias because if we knew the true value of the parameter, there'd be no need to estimate. But the bias is more of a concept that we used to try and minimize. Now, we say here it is the difference between its expected value and the true value. Now, the variance of an estimator is a measure of spread across many different samples. So if you were to repeat this experiment with lots of different samples from the given population, and in this case, our sample is going to be a sample of image data, right? So our estimators are going to be all the different weights and biases that we need to learn. How are we going to measure the bias and variance? Even if we can't get an exact value, how are we going to balance the two? And it turns out these things don't usually go hand in hand. They kind of oppose each other, right? And the reason for that is because, well, if you have a really strong bias in terms of a very low bias, so let's say your model was extremely accurate for a given data set. Now, how do you think that's going to affect the model performance on other data sets, on new data? It might not be as good, right? Because by default, images have such a high variance that any sort of pattern you learn on a specific image data set, if you learn it really well, that might not necessarily extrapolate to other new images. So that's what we need to be careful of. Meanwhile, if we have too much variance, if we try to account for too many different samples of images, we're not going to get a really accurate prediction for each one. So this is kind of our dilemma. We say the more we try to optimize our performance, the less generalizable our model is, and vice versa. The more generalizable we try to make our model, we kind of lose a bit of precision or accuracy on a particular data set. So that's a considerable problem in the machine learning domain. So as the saying goes, there's no free lunch, right? Sometimes less is more. Now, what do we mean by that? So we're going to go over one way that we can optimize performance and generalizability. So one way we can optimize performance is employing a solid architecture, right? So you don't want to have, like, you can learn all about convolution and max pooling and all these different operations, but they don't really have much meaning if they aren't structured in a solid workflow, right? So you want your data to flow nicely from input to output, end-to-end model development, right? And so that's why we say, well, in our model architecture, immediately we're going to normalize our data, right? And we're going to do this at the start of every single sublayer of this model before we do convolution, because we don't want to be convolving or trying to analyze data that hasn't been normalized for reasons discussed. We want to minimize our variance as much as possible before analyzing this data. Okay. So to an extent, introducing a large number of parameters allows the models to be more observant on input data, thus generating more accurate predictions. So obviously, if you had a really simple model like y equals mx plus b, that's probably not going to do much for you when you have complex data sets. But at the same time, sometimes less is more. So over-analysis of the input data is often referred to as overfitting. This means that you're learning very specific patterns of the image data set because you're training on it so much and because you have way too many complicated parameters in your model. So you kind of want to draw a balance between what is the right number of parameters and what are the right hyperparameters. This is an optimization problem that machine learning scientists still try to solve to this day. There currently is no rule of thumb. You just kind of have to either do trial and error or make educated guesses as to what works best. So I've made an educated guess here and said, well, my general idea is if I was a model, first I would want to normalize my data, obviously, and then take 32 features. From that, I want to split each of those features into two new features to get a total of 64. Then do the same thing for 128 to 256. So now at the end of this process, I will have a whole 256 important features of this image to choose from. Right? So that's where we end here. This is our convolutional block, and the convolutional block consists of a normalization layer, a convolution layer, a max pooling layer, and this thing called dropout. Now, dropout helps to prevent overfitting because it randomly drops out 30%, as indicated here, 30% of the input data. And what that allows us to do is, actually, I'm going to start running this now, just because we're a little bit tough on time here. But the important thing I want you guys to realize is that dropout is important because it helps to reduce overfitting. And remember that overfitting is caused when a model overlearns patterns in the data set. So if you randomly drop out certain data points, then the model, it makes it harder to learn or to overfit on particular patterns in the data set. So that's the purpose of the dropout layer here. So I have these convolutional blocks. So after the first 4 blocks, we can see that we have 256 important features of the image to choose from. So that's the format of our image currently. Now I'm going to downscale. So from those 256, re-choose the 128 most important features, then choose the 64 most important from those 128. Then from the 64, I will choose the 32 most important features. Finally, we need to be able to convert this set of information into a prediction, right? And so right now, it's kind of shaped like a box, right? In particular, this box has a dimension of 32, and it has 2 other dimensions. Now we need to get this from 3D to 1D. So we're going to flatten it, which kind of unrolls this tensor of information all into one single vector. And from that vector, we are going to choose, we are going to turn this into a 1 by 19, right, row vector. And as we can see, we see here, this dense layer, which means that every single neuron in the previous layer is connected to every single neuron in the current layer. This dense layer has 19 options to choose from. And the idea is that ideally, we want our model to have this structure so that it can choose 0 as a value for all of the values in this prediction vector, except for the index that it thinks is the best choice for the classification model. So as an example, if we had Bart Simpson was encoded to the integer 0, then we will want this to predict a prediction vector of 1, 0, 0, 0, etc. Okay. So a few other things to note here. tf.keras.optimizers, we do have a class called an optimizer in TensorFlow, and this kind of performs the gradient descent for you. So we set the learning rate here to 0.001, and the 0.001 here represents what is the amount of baby step you're going to take in the direction of steepest descent down this hill, which we call the loss function, right? We're trying to minimize this error function. So we say, take the gradient or the steepest descent direction and take a step of 0.001 in that direction. So it's a very small step, right? We don't want to go too far. Now, the loss function here is binary cross entropy. This is the loss function that we're trying to minimize, either using multivariable calculus or just other methods of numerical gradient descent. So then we're going to compile this model, and the compile method basically says, all right, we're going to summarize this model into like an object, and the optimizer will be as specified. The loss function, which we're trying to minimize using the optimizer, will be as specified. And we're going to measure some metrics, right? And the metrics here, obviously, we want accuracy because this is a classification model, right? So classification, we can define the notion of accuracy. And then we call model.summary to look at our model summary. So as you can see, this kind of lists the number of parameters. And I want you to take a look at this. 780,000 parameters. 780,000 parameters total in this model. It's pretty huge. Although surprisingly, that's kind of small compared to some other machine learning models we'll see in real life, but this is kind of a simple workshop. So I don't want to introduce too many parameters here. But now I want you to notice, we are calling history equals model.fit and all this stuff right here. What does this line actually mean? So let's run through it component by component. So model.fit is the method you use to train your model on the training data specified. So here we have xtrain and ytrain. So xtrain is filled in for the argument that is supposed to be the x training data, so your training input. This is your training labels. So these are the values that you want your model to predict. And your model is going to compare its own prediction to these labels afterwards and compute a loss value using binary cross entropy. Then I'll use the optimizer that we specified to perform gradient descent. Now, we set batch size equal to 10 here. There's really no rule of thumb as to like batch size. And batch size, what that means is that you want to split up your image data into batches. Traditionally, it's kind of inefficient and ineffective to feed your model all the image data set as one whole array or each image one by one. You want to be able to feed your model these images in groups or sets of equal size. And so these sets of equal size, in this case, sets of 10, is called batches. So the best way to figure out what the batch size would be, in my experience, I've just done trial and error, but I'm sure there are studies that indicate a way to make an educated guess about batch size. Similarly, we're training this for 50 epochs. Epochs are the number of training iterations. So what this is doing right now in each epoch is it's saying, out of the 168 batches of size 10, compute the accuracy for each of these batches, take the average accuracy, and then also you want to validate this model, right? What does validating means? Well, validate means what is the accuracy on a new data set it hasn't seen before, right? And the nice thing about this is that, well, TensorFlow models are not going to remember the validation data they've seen beforehand, right? And they are optimizing with respect to the training data. So this is actually good for us because you say in the process of optimizing on the training data, how well does this model perform on other data sets that it has not seen before, right? And so far we can see that, okay, the accuracy for the training data on this model is a little bit more than the validation accuracy, right? So that means we're very, very slightly overfitting the model on the training data, which is okay because this difference is not too huge in this context. One thing I want to note is that there is a difference between loss and accuracy. So it's not necessarily the case that the lower the loss, the higher the accuracy. Sometimes that's not the case, and this is due to the bias variance trade-off. So if you were to have a low loss value, which means a very, very small amount of error, but your accuracy remains the same, that could be an indication that your amount of bias, so let's say you had a really high accuracy, so low bias, is staying the same, but you are now decreasing the variance. And that's called overfitting, right? That's called overfitting your model on this training data set, because now chances are you might not be able to perform so well on the other image data sets that you give it. So I want you to see how fast this thing is running on a GPU, right? And we only got 5 minutes here left, but last thing I want to say is this model is performing really fast on a GPU, right? 20 seconds per epoch. And we can already see a huge increase in our validation accuracy, right? So from 5% to 47% in just 10 epochs. Now, don't get your hopes up because this rate of increase will very quickly drop off once you get to later epochs. Why? Well, because the optimizer is doing its work with gradient descent, right? And so once you start to reach a local or even global minimum, we start to see a decrease in the amount of updates that we give each of our parameters. Why? Because, well, the parameters are already close to their optimal values. So that's why we kind of see like a decrease already in our rate of change. And unfortunately, I had some extra code that we didn't get to hear, but hopefully this will finish training during our Q&A session, and we will be able to have that now. So are there any questions? Actually, no, let me go back and see if there's any questions here. So is the Google Collab posted somewhere? Yes, it should be accessible now, the link. I've changed the sharing properties. Where can I get access to the Google Collab? This link should be in the workshop channel of the Discord. And it is about 2:27, so I just want to conclude this workshop by giving a huge shout out once again to Theo Liu for reaching out to me and inviting me, and a huge shout out to you guys for being willing to attend this workshop and learn a little bit more about how to construct your first neural network. Quick question here, does a batch just contain the prepared image files? Yes, well, yes and no. So the X batch would, but a batch in general contains the image files and its label. So for example, if you had a prepared image file that was a NumPy array, and in the second element of that tuple, you would have the Y label. So that would be that encoding of 19 bits, each of which can either be 0 or 1. And depending on which integer you've encoded your image to, so for example, if you encoded your image to 0 or 1 or 2, all the way from 0 to 18, you would set that corresponding index to 1. So for example, you might have 0, 0, 0, 1, blah, 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 blah. So that would indicate that you have encoded the class of this image to 4. What problems have you generally come across as you've been working with neural networks? That is an amazing question. Honestly, one is just training time, honestly. It's because when you're training with 100 epochs or 200 epochs, it's kind of hard to determine how long it's going to take to train and how long it's going to take to optimize this model. On top of that, there's really no rule of thumb right now to optimize hyperparameters. There's no sort of backing calculations you can do. For me, it's just been sort of trial and error because I still have a lot to learn about machine learning as a field, and I still need to obtain more experience. But in my experience that I have so far, it's mostly been just trial and error, honestly. And that's kind of the fun. That's kind of the fun of it too, is watching your model learn and grow as you make more educated guesses. So for example, the reason why I added this dropout layer, once I increased the dropout rate from 0.2 to 0.3, so 20% to 30% of the data is being omitted randomly every single time, this actually significantly reduced the amount of overfitting on my model. And you can see here for our model, we can determine if it's overfitting if the accuracy for training data is much, much higher than the validation accuracy. What that means is that your model is learning really well the training data, but it can't generalize to new data. So that's kind of a problem I've been dealing with, and that closely relates to the bias variance trade-off. Great question. And it is 2:29, but unfortunately, this model, it took a little bit longer than I expected to go through this workshop, but I do quickly want to highlight the ratio between the accuracy and the validation accuracy. We see that the ratio is pretty close to 1. So I would say I'm pretty satisfied with the performance of this model in terms of overfitting and generalizability versus performance. Last time I ran this script, I was able to get notebook, excuse me. I was able to get around like an 80% accuracy. Maybe at the end, I'll see if this is the case, and I'll see if I can kind of copy and paste this output to give to you guys so that you can see actually how the results turn out. Okay. But thank you so much for attending this workshop, and I really appreciate you guys being so attentive and asking lots of great questions. Theo, was there any last minute words you wanted to give? And again, I'll post this on the, I should have posted this on the Discord workshop channel. You can definitely find it there. Honestly, I'm pretty free this weekend, so if you guys have any questions or are curious about neural networks, I am more than happy to chat about it. I could go on about this topic forever and ever. And with that, I think that is the end of our workshop. Dope. Very nice. Thank you. I see you are a Simpsons fan as well. All right. Thank you so much, everyone, for an amazing time. And best of luck to your hackathon this weekend. I look forward to seeing all the amazing projects you guys come up with. And yeah, that's it from me. Cheers, everyone. Bye. Just take the Q&A real quick.